The process of integration is attempting to help us to reverse the process of differentiation. For example, if let's say we have y is equal to x squared, differentiating this dy dx, this is going to be equal to 2x. So if I were to apply the process of integration to 2x, I will be expecting the result to be equal to x squared. The notation looks like this. Integrating to x with respect to x. This is going to be equal to, since it's the reverse process of differentiation, it is equal to x squared. This is true provided that you already know that the original expression for y is equal to x squared. But in the exam, very unlikely you're going to be having your original expressions all the time. Most likely you will be just required to integrate 2x. But if you were to just integrate 2x and expecting your answer to be this x squared, there is a flaw. Let me explain to you what flaw we are going to be expecting. Because when I have y to be equal to x squared, when I differentiate it, I'm going to get 2x. Okay, this is true, but what if y happen to be equal to, let's say, x squared plus 7? What do I get when I differentiate this? I will still be getting 2x. What if I have y is equal to, let's say, this minus 100? What do I get when I differentiate this? I will still be getting a 2x, which means that unless I know specifically what is the original expression, or else if I'm given just dy dx, what I will be expecting is that in the original expression there can be this constant. Okay, there can be this constant, which I don't know whether it is there, but I know that if it is a constant, when it goes through the process of differentiation, that constant will disappear. So I need to take into account of the possibility that there's this constant. That is why if I were to be given just 2x and I'm supposed to integrate 2x, my answer is going to be equal to x squared. And to take into account of the possible constant that can be that was originally there, we need to add in an extra plus c. This plus c is called the arbitrary constant. This is super necessary. It is very critical for you to write down this plus c, or else if you were to miss this out in an exam, I am very sure, okay, you guys are going to lose marks for it. Okay, so far we have looked at the notation for integration, and we have looked at this plus c, which is like super critical constant, or I can see this c as critical. Okay, we need this in our exam. But how do we actually carry out the process of integration? To carry out the process of integration, it is actually very much similar to how you have differentiated. You'll be using rules, some of the rules which I've highlighted in the outline here, and you're going to be using also results that is in the table over here. Rules, for example, if we have a k, where k is a constant multiplied to that function, and we are supposed to integrate this, k can be taken out of the integration notation. For example, if we have this, integrating 4x cubed, and if I were to be integrating this 4x cubed, this 4, which is a constant, it can be taken out of the integration notation. So I'll be integrating just x cubed. Another one is this plus or minus. If I were to be integrating fx, an expression, plus or minus integrating, plus or minus another expression, if I were to be integrating this, I can actually break this up into two integrals. Integrating the first expression, fx, plus or minus integrating the second expression, gx. It is the same for 3 expressions or 4 or 5 expressions being added or minus one from another. And on top of these rules, we'll be using results. We have a huge list here, and you're supposed to memorize all of them. It's not that bad, okay, although you are seeing a lot here, but after a while, it's actually quite easy to memorize, especially if you have done enough practice on your integration. Most likely, this is going to be just internalized as you practice. Okay, so not to worry too much about the memorization, but you will need to memorize definitely. So let's take a look at some of the results here. For example, if I were to be integrating a constant, okay, then integrating a constant is going to be ax plus c. This is pretty easy to explain because if let's say we have y, to be equal to ax plus c, this is the result of integration. That means we are trying to reverse the process of differentiation already. So to just do a very quick verification, we can just definitely do a differentiation to verify. So what do I get when I differentiate this? I'm going to be getting an a. That is why if I were to be integrating a, then it will be equal to ax plus c. It is like here. Integrating 2 dx, it is like 2x plus c. Another one that we have is this, integrating x to the power of n, where n is not -1. If n is -1, we actually need to make use of another formula, which is this. Okay, this is when n is -1. This 1 over x is like x to the power of -1. So the result is going to be equal to ln x. But if n is not -1, then integrating x to the power of n, it will be x to the power of n plus 1 divided by n plus 1. We can actually apply it to this. Okay, let's say we don't know this. So let me erase this. Okay, we don't know. Okay, we don't know that this is going to be x squared plus c. So what am I going to be expecting when I integrate this? So 2, I can take it out of the integration notation. I'll be integrating x. The x and x, I can see it as x to the power of 1. And since 1 over here is not -1, so this, according to the result that we have here, is going to be 2. Then x to the power of 1 plus 1 divided by 1 plus 1 plus c. So this is going to be equal to 2. X to the power of 2 divided by 1 plus 1. This is also 2 plus c. 2 can be cancelled. This is going to be equal to x squared plus c. So it is the same here. When we try to integrate x to the power of 3, it is going to be x to the power of 3 plus 1, which is 4, divided by 3 plus 1, which is also 4, plus c. We have another variation. Okay, this looks, I mean, you have to memorize this, but actually this looks very, very similar to the previous one. Let me show you the similarity, because it is almost as if x is being replaced by a linear expression, ax plus b. So when x is replaced by this linear expression, ax plus b, it will be the same. The result will be like x being replaced by ax plus b. So it will be ax plus b to the power of n plus 1 divided by n plus 1. We have it here. Ax plus b to the power of n plus 1 divided by n plus 1. But on top of that, we will divide it by the coefficient of x, which happen to be a. So if I have integrating, if I'm supposed to be integrating 5x plus 3 to the power of 5, then it will be like 5x plus 3 to the power of 5 plus 1, which is 6 divided by 5 plus 1, which is also 6. Then divide it also by the coefficient of x, which happen to be 5, then plus c. Let's always remember this plus c. If I were to be integrating e to the power of x, it is going to be e to the power of x plus c. This is obvious, although this looks a bit weird, but this is obvious because if y happen to be equal to e to the power of x plus c, what do I get when I differentiate this? Y is equal to ex plus c. When I differentiate this, I will be getting e to the power of x, which is this. E to the power of x. Extending this to when x is being replaced by a linear expression, just like what we discussed previously. So when x is replaced by a linear expression, then it is going to be e to the power of ax plus b divided by a. Just like this. Okay, we have a e to the power of 4x plus 7, so it will be e to the power of 4x plus 7 divided by the coefficient of x, which is 4, and this plus c. And what if we have this? 1 over x, this is equal to ln x, right? Because when I differentiate ln x, it is going to be equal to 1 over x. So when I integrate 1 over x, it is going to be ln x, but not just ln x, because we don't know whether there was a constant that is before in the original y's expression, so we need to put in this extra plus c. And if x is replaced by a linear expression, ax plus b, then the result is going to be ln ax plus b, then divided by the coefficient of x, so divided by a, then plus c. For example, if I have this, integrating 1 over 3x plus 8, it is going to be ln 3x plus 8 divided by 8 plus c. The same goes for these few trigonometric integrals here. So if I have a sine x, integrating this is minus cosine x plus c. And if I were to replace x by ax plus b, then it will be minus cosine ax plus b divided by the coefficient of x, which is a. The same goes for this. Okay, cosine will become sine. Cosine ax plus b will become sine ax plus b divided by a. And finally, secant square will become tangent x, because when I differentiate tangent x, I'm going to be getting secant square. So I have this, and if x is replaced by ax plus b, the result is going to be tangent ax plus b divided by a plus c. But for trigonometry wise, what you will realize is you may, okay, not always, it is not always necessary, but you may need to apply some trigonometric identities. So I'm showing you 3 examples here, and I think these 3 examples are very, very good examples. So please take note of this, because in exams we see this pretty often, okay? So what if we are supposed to be integrating sine square? Let's try it together. So we are supposed to be integrating sine square x. So to integrate this, the first thing that we want to do is to go through the list. Okay, but if you were to go through the list, there's one that is similar, which is maybe this sine x here, which will give us a negative cosine x plus c, but sine x is not the same as sine square x. So we will not be able to find anything from the list of results that we can be applying to this, and this is when we need to revisit our list of identities. Let's take a look at what we have in our formula sheet. So in our formula sheet, revisiting the identities, and specifically this one here is going to be helpful. Cosine 2a is equal to 1 minus 2 sine square a. So if I were to look at this, cosine 2a is equal to 1 minus 2 sine square a. And if I were to make sine square a the subject, we can actually re-express this. So let's try to do this first. If I were to make sine square a the subject, so bring this over to the left hand side, we have 2 sine square a. This is equal to 1 minus cosine 2a, which means that sine square a is 1 minus cosine 2a divided by 2. So now I can re-express this, and this will become 1 minus cosine 2a, which is going to be cosine 2x in this case, divided by 2 dx. 1 over 2 is a constant, so I can actually take it out of the integration notation, so I will be left with a 1 minus cosine 2x dx. And now we have something that is in our list of results that we can make use of, which is actually this here, cosine ax plus b. It is this cosine 2x plus 0. So now we have a result, and we can start to do our integration. It is going to be equal to 1 over 2. Integrating 1 gives me an x. Then integrating cosine 2x, following this, will give me a sine ax plus b divided by the coefficient of x, which is a. So this will become sine of 2x plus 0, then divided by the coefficient of x, which is 2. Then this, let's not forget the plus c. So my answer should be equal to this. Let's take a look at what if we were to be required to integrate cosine square. If we were to integrate cosine square x, we are going to once again make use of the list of identities, and the identities that I'm going to be making use of will still be this, the double angle formula, but I'm going to be making use of this one here instead. So if I were to list that down, we have a cosine 2a, this is equal to 2 cosine square a minus 1. And I'm going to make cosine square a the subject. So 2 cosine square a, this is going to be equal to cosine 2a plus 1. Which means that cosine square a is going to be equal to cosine 2a plus 1 divided by 2, or if I were to just follow this, then it is also okay to write this as 1 plus cosine 2a divided by 2. So this will help me to re-express cosine square a. So this is going to be integration of 1 plus cosine 2a, okay, this should be x. So 1 plus cosine 2xa is going to be replaced by x. So this divided by 2. And since 1 over 2 is a constant, I'm going to take it off the integration notation, and I'm going to be just integrating 1 plus cosine 2x dx. And now, once again, I have a result that I can make use of. It is still this, cosine 2x plus b. It is equal to, integrating this, it is sine 2x plus b divided by the coefficient of x, which is a. So applying that to here, we have a half. Then integrating 1, it is going to be equal to x. Then integrating cosine 2x, it is going to be sine 2x divided by 2. Then this plus c. One more that we are going to be making use of identities. I really need you to get used to applying identities to manipulate an expression before you can actually carry out the process of integration. So one more example that I'm going to give you here, it is still going to be a good example, as good as the two previous ones that we have done, which is what if we were to be required to integrate tangent square. Okay, let's try. So in this case here, we are going to be integrating tangent square of 2x plus 1. Okay, and we will not be able to find any results that is in our list that can help us to directly integrate tangent square. So I'm going to once again make use of trigonometric identities, and the one that I'm going to be making use of will be this. Secant square a is equal to 1 plus tangent square a. So let me write it down here. Secant square a, this is 1 plus tangent square A. And since we are dealing with a tangent square which we want to manipulate, I'm going to make tangent square the subject. So tangent square A is going to be equal to secant square A minus 1. And this will actually help us to integrate this over here. Let's try. So for this is going to be re-expressed through the application of the trigonometric identity into the form of secant square A, which is going to be replaced by 2x plus 1, then minus 1. So integrating secant square 2x plus 1, I'm going to be making use of this. Okay, secant square ax plus b. The result is going to be equal to tangent ax plus b divided by a. So this will be tangent of 2x plus 1 divided by 2. Then minus integrating 1, it is going to be equal to x. And let's not forget about the plus c. These are the few examples that we have looked at. Integration definitely requires us to do a few more practice, so let's try some more questions together. So let's try some of these questions together. Let's take a look at this here. So for this, question number 1a. 1a, we have this to be integrated. So 2x squared plus 1, 4x minus 3 dx. Please take note that this is not the same as integrating 2x squared plus 1 dx multiplied by integrating 4x minus 3 dx, okay? Because we have no rules that are like this. We have the sum and difference rule. So plus or minus an expression, so integrating plus or minus, integrating an expression plus or minus another expression is like integrating one expression plus or minus another expression. But when one expression is multiplied to another expression, it is not integrating one expression and then multiplying the other expression, okay? It is not. So in order for us to overcome this and yet being able to still make use of the list of identities, list of the results here, we are going to manipulate this by expanding this. So if I were to expand this times this gives me a 4x to the power of 3. This minus 6x squared, this times this, plus 4x, this minus 3 dx. And now we can make use of integration to making use of the results that we have here to integrate this. And I'm going to take out constants for terms that are like this, 8 minus 6, 4. And I'm going to be making use of this x to the power of n, which when I integrate this, it is going to be x to the power of n plus 1 divided by n plus 1. So this is like 8, then integrating x to the power of 3 dx, then minus 6, integrating x squared dx plus 4, which is a constant, and I'm taking it out of the integration notation, then dx minus 3 integration of 1 dx. Okay, this can feel a little bit weird, but it is an official notation. If you want to re-express this, okay, you can take out 3, and it is supposed to be a 1 here, right? But it is common not to even write the 1 at all. Okay, so this, when you don't see anything inside this integration notation, it represents that there is going to be a 1. Now, of course, you can still leave the 3 inside. It is no problem. Okay, but anyway, this is still okay. So this is going to be equal to 8. Integrating this, we have x to the power of 4 divided by 4 minus 6. Integrating this, x to the power of 2 plus 1, which is 3 divided by 3. Then plus 4, integrating this was x to the power of 1. So it's going to be 2 divided by 2 minus 3, integrating 1 is going to give me an x. Then this plus c. And if I were to just multiply this in, I'm going to be having a 2x to the power of 4 minus 2x to the power of 3 plus 2x squared minus 3x plus c. Let's take a look at b. Let's see what we have here in b. b, we are supposed to integrate this. So for 1b, we are supposed to be integrating this x to the power of 3 minus 1 divided by x to the power of 3 dx. And I'm going to manipulate this into integration of x to the power of 3 divided by x to the power of 3 minus 1 over x to the power of 3 dx. And similar to a, this is not the same as, this cannot be expressed as integrating the numerator divided by integrating the denominator. Okay, again, there's no such rules, so we got to manipulate it this way. Then it is going to be this divided by this is 1. Minus this, I'm going to write it as x to the power of minus 3. And integrating 1 is going to be x. Integrating this is going to be x to the power of minus 3 plus 1 divided by minus 3 plus 1, then plus c. So my final answer is going to be here, is going to be x to the power of minus 2 divided by minus 2 plus c. This is going to be x plus 1 over 2x squared plus c. Let's take a look at another one, c. In c, we are supposed to integrate this. 1 over square root of 5x plus 2. And I'm going to re-express this as integration of 5x plus 2 to the power of minus half dx. And what I'm going to do is to apply this over here, this one over here. Okay, so if I were to apply this, then this will be 5x plus 2 to the power of minus half plus 1 divided by minus half plus 1. And let's not forget to divide it by the coefficient of x, which is 5, then this plus c. So my final answer is going to be equal to 2 over 5, then 5x plus 2 to the power of half plus c, which is equal to 2 over 5. I can also re-express this as square root of 5x plus 2, then plus c. Let's take a look at another one. So let's take a look at question number 2, and we have this. Okay, we are supposed to integrate this. So we are supposed to be integrating e to the power of x minus e to the power of minus x squared dx. Let's take a look at the list that we have here, and I think I'm going to be probably applying this, but I cannot apply this directly, so I need to do a bit of manipulation to this. So what I'm going to do is I'm going to expand this. So expanding this will be e to the power of x squared minus 2 times of this e to the power x multiplied by e to the power of minus x, then plus e to the power of minus x squared. So we'll be integrating e to the power of 2x minus e to the power x times e to the power minus x gives me e to the power of 0. So I'll be left with just 2 times e to the power of 0, which is 1. Then plus this is e to the power of minus 2x dx. And now I'm going to be applying this over here, ax plus b, e to the power of ax plus b. So applying it to this, it is going to be e to the power of 2x divided by 2 minus 2, integrating a constant. I'll be applying this. So this will be 2x. Then plus this will be e to the power of minus 2x divided by the coefficient of the x. So it's minus 2, then this plus c. You may be wondering, okay, what if I were to be integrating this, right? Wouldn't I have a plus c? Then if I were to integrate this, this will have another plus c, and this will have another plus c. So there should be 3 c's, correct? But this c is an arbitrary constant. It represents a constant. So regardless of whether it is c1 plus c2 plus c3, if you are imagining every single integration gives you a c, so c1 plus c2 plus c3, or you can just consolidate them and just simply write it as one single plus c. They are going to be correct. Okay, it is just representing an arbitrary constant. Okay, so although we are integrating it 3 times, and in the previous few questions we have actually been doing that also, we can consolidate all the c to become one single c, one single arbitrary constant in my final answer. So this is going to be equal to, I'm going to just write this as half. So half e to the power of 2x minus 2x, this will be minus half e to the power of minus 2x plus c. Let's take a look at another question. It is this over here. Let's take a look at this, an interesting question. So in 2b, we are supposed to integrate this 2x minus 1 divided by 2x plus 1. Okay, we are supposed to integrate this, and we do need to carry out a manipulation. But to manipulating it to what? Manipulating it to something that we know we can apply one of the results to integrate. And one of the results that I know I can be making use of is actually this under the logarithmic part. Because if I can just manipulate this by doing a long division. Why do I want to do a long division? Because the expression that I see here is an improper expression. So it is x power x, x to the power 1, x to the power 1, so this is improper. If it is a proper expression, then it will be something like a constant over x or x over x squared. So if it is x over x or x squared over x, these are considered as improper and you will justify you carrying out a long division process. Or if you are for this particular case, if you are too lazy to carry out the long division process, you can also do simple manipulation that is like this. Since I have a plus 1 in the denominator, so I'll do a plus 1 minus 1. Okay, that is actually 2x. And there's still this minus 1 here, let's not forget about it. So I have a 2x plus 1 dx. And now we have a 2x plus 1 minus 1 minus 1. This is minus 2 divided by 2x plus 1. This will be, this divided by this is 1 minus away 2 over 2x plus 1. So integrating 1, it is going to be equal to x minus 2. This is a constant, so I'll be integrating 1 over 2x plus 1, which will be ln of 2x plus 1 divided by the coefficient of x, which is 2. So I have this plus c, and my final answer is going to be x minus ln of 2x plus 1 plus c. Let's take a look at another one. And the other one is going to be this. Question number 3 over here. So in question number 3a, we are supposed to be integrating 1 plus 4 cosine cube x divided by cosine square x dx. Okay, and this will definitely require me to involve the trigonometric the integration. So I'm going to be looking at this list over here. Okay, so for this, I am going to break it up into 2 parts. The first part will be 1 over cosine square x, and the second part will be 4 cosine cube x divided by cosine square x. And what is 1 over cosine square x? This is secant square. Then plus 4, this will be cosine x dx. And what am I going to be getting when I integrate secant square? Integrating secant square gives me a tangent x. So this will be tangent x. And how about cosine x? Integrating cosine x gives me a sine x. So for this, it is going to be plus 4. This will be sine x plus c. One more, 3b. 3b. Okay, let's integrate this. So in 3b, we are supposed to integrate sine 3x cosine x plus cosine 3x sine x. Okay, this looks like a huge expression to be integrated, but if you were to look at the formula, the identity list, okay, let's look at it again, you realize how similar this is to this particular identity over here. Okay, and specifically the one that I'm going to be making use of will be sine a plus b. But let me write down the right hand side to be equal to the left hand side instead, so that visually it is easier for me to explain to you this. So on the right hand side, it is going to be sine a cosine b plus cosine a sine b. And this is the same as sine a plus b. And can you see that a here is like 3x and b here is like the x. So sine a cos b plus cos a sine b, this is going to be equal to sine a plus b. So this will be equal to sine of 3x plus x. And this is like integrating sine of 4x dx. And do we know how to integrate sine 4x? Yes, we do, because in the list that we have here, sine ax plus b, when I integrate this, is minus cosine ax plus b divided by a. So this will be minus cosine of 4x divided by 4 plus c. Let me introduce you to another kind of integration, which is called the definite integral. Because so far what we have done here, they are all called the indefinite integral. And when it is a definite integral, okay, it is a definition that is here. This will become more meaningful later when we talk about how we can apply integration to find areas. But for today, we're going to be just looking at this as a rule. So for definite integral, we have this. Okay, let me zoom in a little bit. So for definite integral, we have this rule. Okay, it's actually pretty easy to apply if I were to be integrating fx. And I get this another expression, which I'm using the capitalized F for the function. So integrating this gives me this plus C. But if I were to have these two small little numbers over here, okay, at the bottom and at the top of the integration notation, the one that is at the bottom is called the lower limit. The one that is on top is called the upper limit. So if we have a lower limit as A and upper limit is B, integrating this, we will still make use of the same expression, fx, but we will not write in the plus C. We will replace this plus C by a square bracket. Please take note, it must be a square bracket, not a curved bracket. Then A and B, I'm going to continue to write them, but in this way. Then after that, I'm going to substitute B into the expression of the capitalized F function. Then minus away, substituting A into the capitalized A function. It's going to be subcapitalized F function. So, and it's going to be this. An example that I'm going to give you will be this: integrating x squared dx. What do I get when I integrate x squared? It is going to be x to the power of 3 divided by 3. But we are looking at a definite integral case. So the lower limit is 2 and the upper limit is 5. So although we know that it is x cubed divided by 3 plus c, we will not write the plus c. We will replace the plus c by a square bracket, 2 to 5. And then we will substitute the upper limit in, minus away the lower limit. This gives me a 39. So the result of a definite integral will actually be giving us a numerical result. For an indefinite integral, which we have been doing all the while in the previous part, is going to give me an expression, then plus c. Let's take a look at examples for definite integrals. Let's take a look at this question number 4. So in question number 4 here, 4a. For a, we are supposed to integrate from minus 1 all the way until 2 of 2x to the power of 3 dx. And we know that if this were to be a indefinite integral, okay, if I were to eliminate this minus 1 and 2, so integrating 2x to the power of 3 dx, this is going to be 2 integrating x to the power of 3 dx, which will be 2x to the power of 4 divided by 4, then plus c, if this were to be an indefinite integral. But with a lower limit of minus 1 and an upper limit of 2, this will be, when I integrate this, it is going to be 2, then x to the power of 4 over 4. Instead of writing a plus c, I will replace it with a square bracket, then minus 1 to 2. And it will be this, if I were to just simplify, x to the power of 4 over 2. From minus 1 to 2, then I will substitute the upper limit in, then minus away the lower limit being substituted in. So it will be x being replaced by 2, so it will be 2 to the power of 4 over 2. Then minus away, minus 1, substituting in to the power of 4 divided by 2. And my answer here is going to be equal to 15 over 2. Let's look at B. B, we are supposed to be integrating from minus 8 to minus 1. Of 11 e to the power of minus 2x over 3 dx. So 11, it is just going to be as it is. Integrating this, it will be e to the power of minus 2x over 3 divided by the coefficient of x, which is minus 2 over 3. And I'm going to replace c with the square bracket, minus 8 as the lower limit and minus 1 as the upper limit. So for what we have here, this is going to be evaluated to minus 33 over 2. I can write it inside the bracket, or you can actually take it out of the bracket. Okay, it really depends on you. Let's say I prefer to take out this minus 33 over 2 out of the square bracket. So I'm going to write it as this, minus 33 over 2. Then e to the power of minus 2x over 3 from minus 8 to minus 1. Minus 33 over 2 will stay as it is. Substituting this in, we have a e to the power of minus 2 times minus 1 over 3 minus e to the power of minus 2 times minus 8 over 3. And pressing this into the calculator, rounding it off to 3 significant figures, it is going to be 3390. Let's take a look at one more example, which is here, C. So in this one last example for C, we are supposed to be carrying out a definite integral from minus pi over 3 to pi over 3 of this sine x, cosine x, dx. And sadly, we will not have a result that we can apply to this. So this is when I'm going to revisit my trigonometric identity list. And from the list, I'm going to be choosing this. sine 2a. Let me write it down here. Sine 2a is equal to 2 sine a cosine a. Okay, we are going to be making use of this. And what we are going to do is to try to simulate this sine a cosine a as this sine x cosine x. So sine a cosine a is going to be equal to sine 2a divided by 2. So I'm going to rewrite this here from minus pi over 3 to pi over 3 as sine 2x divided by 2 dx. 1 over 2, I can take it off the integration notation, regardless of whether it is a definite integral or indefinite integral, I can still take out the constant. So I will have this pi over 3, and we are supposed to be integrating sine 2x. And to integrate sine 2x, we can now refer to what we have in the list of results that we have here. And I'm going to make use of this sine ax plus b, which means that this will become minus cosine 2x divided by 2. So this will be 1 over 2 square bracket. This will be minus cosine of 2x divided by 2 from minus pi over 3 to pi over 3. So let's say this 2, I'm going to take it off the integration, including this minus half. Okay, I'm going to take out minus half, okay, including this minus 1. So I'm going to take out this, it will become minus 1 over 4. And we are supposed to be integrating cosine, it has already been integrated. We are supposed to be dealing with this as the integral. So we have this cosine 2x. So I'm going to substitute values in minus 1 over 4, which will give me a cosine 2 pi over 3 minus cosine of minus 2 pi over 3. And we know in our trigonometric transformation that cosine minus theta, okay, cosine minus theta is the same as cosine theta. So if I were to apply the trigonometric transformation to this, or of course you can just press it to the calculator also, but if I were to apply the trigonometric transformation to this, it is going to be minus 1/4 of cosine 2 pi over 3 minus away this, which is also going to be cosine 2 pi over 3. So this is going to be this minus this. It is going to be minus 1/4 times 0. So my answer here is actually 0. Let's take a look at this question number 5. It is an interesting question because it is a twist from what we have been doing previously. We are given this. When we integrate from a lower limit of 4 to an upper limit of an unknown constant, 3, of 3 over 2 square root of 3x plus 4. This is given to us as 61 over 3, and we're supposed to solve for k. And to do this, let's just carry out our process of integration according to what we have discussed. And in this case, it is for what we have discussed in the indefinite integral. So 3 over 2, I'm going to take it off the integration notation. And I'm going to be integrating from 4 to k. And for this, we are going to re-express this square root as to the power of half. This is 61 over 3. And 3 over 2, I can bring it over to the right hand side, which will give me a 122 over 9. And let's integrate this. Integrating this, it is going to be 3x plus 4 to the power of half plus 1. It is 3 over 2 divided by 3 over 2. And let's not forget to divide it also by the coefficient of x from 4 to k. And this, if I were to multiply it across, I will be getting a 61. So here is going to be 3x plus 4 to the power of 3 over 2 from 4 to k. Now we'll substitute these numbers in just like how we have discussed for definite integral. I'm going to be getting a 3k plus 4 to the power of 3 over 2 minus away, substituting 4 in. 3 times 4 is 12, so 12 plus 4 to the power of 3 over 2. This is equal to 61. This I'm going to leave it as it is. 3 over 2. This can be evaluated. Bring it over to the right hand side. This gives me, this was 64. Bring it over to the other side. This gives me a 125. And I'm going to power 2 over 3 on both the left and the right hand side. So power 2 over 3 on the left hand side gives me this and 125. Power 2 over 3, this gives me a 25. So 3k plus 4 is equal to 25. 3k is going to be equal to 25. Minus 4, this is equal to 21. This tells me that k here is equal to 7. Let's take a look at one more idea that is involving this definite integral. And this concept is more of like a property of definite integral. It can be found here on the last page of my outline. It is this set of properties here. It is just 3 properties that I want to talk about. So the first one here, okay, if I were to be integrating from a to a, it is going to get me a 0. For example, if I were to say that integration of fx dx, this is an indefinite integral, this is going to be equal to fx plus c. So if we were to integrate from a to a of fx dx, then this will be like fx square bracket a to a, which means that it is going to be fa minus away fa. That is why this is equal to 0. And if I were to be integrating from a to b of fx dx, I'm going to show you why the second one looks like this. This is like fx a to b, and according to what we have defined about definite integral, this is fb minus away fa. And this is actually the same as if I were to factorize out negative, which will then give me a fa minus fb. And what is this? This is the same as integration from b to a of fx dx, which gives us the second property. So from here to here, it is like switching the upper limit and the lower limit, a to b, to now b to a, and I'll just need to add in an extra negative in front. And for the last one we have a, let me just start from the right hand side. Okay, I'm going to prove to you this by showing you how the right hand side can become the left hand side. So if I were to look at the right hand side, the right hand side is a integration from a to b of fx dx plus integration from b to c of fx dx. So this is going to be the same as fx, then square bracket a to b plus fx, then square bracket b to c. So this is like fb minus away fa plus this will be fc minus away fb. So fb and fb can be cancelled. I'm going to be left with this and this, but I'm going to write it as fc minus away fa. And what is this? This is integration from a to c of fx dx. So to apply this, or rather to memorize this, I find it easier to just spot this. Okay, the upper limit here is the same as the lower limit on the other integral that I have here. So when I add these two together, I'll be left with the same thing, a to c. Okay, the same thing as in like the inside of the integral should be the same. Okay, if they are different, you cannot apply this also. Okay, so this 1, 2, 3, we will apply them when it is necessary, depending on questions. For example, let me show you one question that will require us to apply this, and let's take a look at this one last question over here. So in this last question here, we have integration from 3 to 5 of fx dx is equal to 8, but we don't know what is fx. We are supposed to work on part 1 and part 2. So in part 1, we have integration from 5 to 3 of fx dx, from 5 to 3. But what that was given to us is this same fx, but it was from 3 to 5. The lower limit was 3 that was given, and the upper limit was 5. And now we have 5 to 3, so applying the properties that we have just discussed, this will be minus from 3 to 5 of fx dx. So this is 8, according to what the question tells us. So part 1's answer is just minus 8. And in part 2, we are supposed to integrate from 3 to 4 of fx plus 3 dx plus integration from 4 to 5 of fx dx. I'm going to break this up into 2 parts, which will be integration from 3 to 4 of fx dx plus integration from 3 to 4 of 3 dx, or you can also write this 3 outside, leaving empty inside, which represents a 1, then plus integration from 4 to 5 of fx dx. And I'm going to put this and this expression side by side, which is going to be from 3 to 4 of fx dx plus this will be 4 to 5 of fx dx. And let's say now this time I decide to take the 3 out, so it will be 3 integration 3 to 4 of 1 dx, which it is invisible, it is there. Okay, so this is a proper notation that we have discussed just now. As for this over here, we can use the third property that we talk about, because this is 4, the upper limit, this is 4, the lower limit. So combining these two together gives me an integration from 3 to 5 of fx dx plus 3, integrating 1 is x, from 3 to 4. So this is going to be equal to, according to the question, this is going to be equal to 8, then plus 3 times of what we have here is going to be 4 minus 3. So 8 plus 3, this is equal to 11. And this is what I have for integration technique. And once you are ready with this, I'm going to see you in the next part of integration.